Hi, I'm Matt, and in this video we are going to go over kinetic molecular theory and ideal gases. So what is kinetic molecular theory? Kinetic molecular theory tells us how an ideal gas would behave, and ideal gases are gases that follow these 5 postulates, which are gas particles have a negligible volume, gas particles move in random straight lines, gas particles do not exert intermolecular attractive forces on other gas particles, collisions between gas particles are elastic, and the speed of a gas particle is proportional to the temperature in Kelvin. That in Kelvin part is very important. So now let's go into detail on all 5 of these. So first, gas particles have a negligible volume. This means that compared to the size of the container, the gas particles take up very little space. So you see the 6 blue dots are gas particles in that flask take up nearly none of the space inside of it. And the other piece of this is that gas particles are separated by a distance greater than their size. The distance between the blue dots is much larger than the dots themselves. Postulate 2 is that gas particles move in random straight lines, not circles. I specifically say that because many multiple choice questions try to trip you up by putting circles as a choice. And the direction they move is random. All it has to be is straight, but it could be in any direction. And the only time these paths stop being straight is when they bounce off a wall or another particle, and then they will just continue in a different straight line. The next postulate is that gas particles do not exert intermolecular attractive forces on other gas particles. In other words, one gas particle does not attract or repel any other gas particle. And as a whole, a gas particle's motion is unaffected by any other gas particle except in a collision. So you see in the diagram there's that one red particle. That red particle is not being affected by any other particle in the flask unless they collide. Postulate 4 states that collisions between gas particles are elastic. This means that when the particles collide, no energy is lost, or the initial energy equals the final energy. So, let's say the green particle has 30 joules of energy, and the red particle has 50 joules. There's 80 joules before the collision, so there has to be 80 joules after the collision. Energy can still be transferred when they collide. Instead of 30 and 50, they could both end up with 40 joules, but the sum will still have to be 80 joules. The last postulate states that the speed of a gas particle is proportional to the temperature in Kelvin. Remember that temperature is the average kinetic energy of a molecule, so at a higher temperatures, there's more kinetic energy and faster movement. And at a lower temperature, there's less kinetic energy, so the particles will move slower. When we compare the energies and speeds, the temperatures must be in Kelvin, not Celsius. Comparison to a Celsius will not be correct. Now, in these 2 flasks, the one on the right is at the higher temperature, and we can see because the arrows are longer. Next up, we have to talk about the differentiation between ideal gases and real gases. Gases tend to violate the ideal gas law for many reasons. Some of these reasons are: real gases have intermolecular forces between them, leading to curved paths instead of straight paths. Real gases have volumes that are often not negligible, and real collisions often don't have elastic collisions and instead have inelastic collisions. So, when do real gases behave most like ideal gases? This is going to happen when we could minimize those deviations on the last slide. So this occurs when we are at high temperatures, low pressure, the gas particles have a minimal volume, and there's minimal intermolecular attractive forces. Now, if you're in a lower level chem class, like Regents Chemistry, you only need to know the first 2 bullets, and at this point, I would encourage you to skip to practice set 1 of questions at the end of the video. If you're in a higher level class, or you're just interested, we're going to go over all 4 of these bullets in detail. So first, let's talk about high temperatures. So on the right, the particles are moving faster, and we could see that because the arrows coming out of them are longer. And remember, at high temperatures, gas particles have very high kinetic energy, and as a result, move very fast. When the gas particles are moving this fast, they can't interact with each other as much, so the intermolecular attractive forces become negligible, due to this high speed, because it's moving so fast that its path will barely curve, because by the time one particle is about to act on it, it's already past that point. While at very low temperatures, the gas particles have a long time to interact with each other and attract towards each other. Next up, gas particles are most ideal at low pressures. So in the flask on the left, we see that there's very high pressure and a low volume, which means the particles are close together. While on the right, there's low pressure and the particles are able to spread out more. So at a low pressure, the gas particles are further apart. And intermolecular attraction is radius dependent. In other words, it's weaker at a farther radius. Therefore, when the particles are farther apart, the intermolecular attractive forces are minimized. Therefore, at low pressure, the gas is most ideal because those intermolecular attractive forces are nearly negligible. Next, we're going to talk about the volume of the gas particles. So on the left, we see that the gas particles take up most of the space in the flask and have very small distance between them. While on the right, the particles are small and are able to stay very far apart. So when we have a situation on the right, that's going to model an ideal gas because the particles have a negligible volume compared to the container and can stay far apart. And remember from the last slide that intermolecular attractive forces are weaker at larger distances. So when the molecules have small volume, they're able to stay far apart and minimize the intermolecular attractive forces between them, making them exhibit ideal behavior. So now the last thing we're going to talk about is intermolecular attractive forces themselves. So when there are strong intermolecular attractive forces, the movement is not ideal because the paths will become more curved as the gas molecules are attracted to each other. Therefore, we want there to be weak intermolecular attractive forces for there to be ideal behavior. Also, if we have strong intermolecular attractive forces, we will end up with inelastic collisions, so the energy will decrease over time. Now, remember that polar molecules have a negative side and a positive side. They have stronger intermolecular attractive forces between them, so generally speaking, polar molecules will deviate more from ideal gas behavior than a nonpolar molecule will. So here I have a short set of practice questions based only on kinetic molecular theory. Question 1 asks about the type of collisions. Question 2 asks what type of movement they exhibit. Question 3 asks about the speed and what unit we use for it. And question 4 asks about the distance between the gas molecules. So I encourage you to pause the video and try these on your own, and the answers will be provided for you on the next slide. So the answers are as follows. According to kinetic molecular theory, when ideal gases collide, they will have elastic collisions. Kinetic molecular theory says that gas particles will move in a straight line. According to kinetic molecular theory, the speed of the gas is proportional to the temperature measured in Kelvin, and the distance between gas particles is greater than the size of the gas particles themselves. Hopefully you got these, and we're going to move on to the second set of practice questions. So here, practice set 2 asks about real gases and the differences between them and ideal gases. So question 1 asks about the temperature and pressure and what's most ideal. Question 2 asks about molecular polarity. Question 3 asks about the collisions and the paths of gas molecules. And question 4 asks about the size of the gas molecules. Once again, I encourage you to pause the video and the answers will be provided for you on the next slide. The solution to practice set 2 is as follows. Real gases behave most like ideal gases at low pressure and high temperature. Nonpolar molecules behave most like ideal gases. And strong intermolecular attractive forces will cause the paths of gas molecules to curve and the collisions to become inelastic. And lastly, gas molecules that take up high volumes deviate most from the ideal gas law and kinetic molecular theory. Hopefully you got these. If not, feel free to leave any questions you have in the comments below. Thank you so much for watching. Have a great day.